Welcome listeners again to the next topic of our discussion, that is groundwater, and it is in the series of discussion or lectures in the fundamentals of geology. So obviously to start with the discussion on groundwater, here I would like to say that groundwater will be ending with that as well later on. We'll see why. The groundwater is not a renewable source of energy, or it is not a renewable resource. So, or I'll not say energy, obviously, it is water that we use in our daily life and livelihood. So, the thing is that it is very important to understand groundwater, how it flows beneath the surface of the earth, how it interacts with the other properties or the subsurface properties, and how it leads to also formation of certain landforms that we will be looking at in the third part or fourth part of this lecture on groundwater. And also finally its importance, that why it is very important, and it's you can say, now I'll simply give you a kind of a quantification that is kind of available, and I can say if I take the total water reserve, be it saline water or your fresh water, including your surface water, groundwater, the permafrost, all these things, then totally, if I say that means you have 20 liters of water in total, then obviously 19.5 liters of water is occupied by your saline water. Then the rest of the half liter that is only left, out of that also about 125 ml of water is only left as your fresh water, because the rest of the water, around 375 ml of water, with respect to the 20 liter of total water on earth, just I am saying just to decrease the scale, and it will help you to understand that how important it is. And so about 375 ml of water is present as ice sheets in your permafrost regions, be it in your Antarctica or in your Greenland. And then the rest of the 125 ml of water, that is also divided into your subsurface and surface water. Surface water means obviously streams and rivers, and you have groundwater in the subsurface. So approximately for fresh water use, if I use means if I want to use groundwater for drinking purposes and other purposes as well, be it in some industry, be it in your regular household activities, then approximately out of that 20 liters of overall water on earth, you have only 5 drops of groundwater available to you for your daily use. So it is approximately about 0.005 or 0.007% of the total water available on earth. So obviously we are not looking into the water that is present in the mantle. Apart from that, whatever water is lying in the crustal part, so we are referring to that kind of water here. Means surface water, saline in oceans, then your permafrost regions, and obviously the groundwater, which is the topic of discussion here. So dealing with groundwater, it is very important to first understand the subject, that is hydrology, that is obviously the science of studying water. And geohydrology deals with, specifically whenever we are adding this term geo, that means it is the hydrology of the earth that we are referring to. So it encompasses two main aspects, that is movement of the groundwater or movement of the water and occurrence of the water. Here again and again we are referring to groundwater, because now that will be our focus of our discussion. So any measurements within hydrology come under the domain of hydraulics, but the reverse is not true. Flow of water come under hydrology, but its measurements such as velocity come under hydraulics. So you can see why the reverse is not true. Now groundwater also refers to the water that is stored beneath the earth's surface in soil pores and in the fractures of rock formations. It primarily originates from the precipitation that infiltrates the soil and percolates downward until it reaches a saturated zone. Again, these are the two terms, infiltration and percolation. So, percolation means movement of water within the soil, infiltration means the movement of the water through the soil. It also comes from surface water bodies such as lakes and rivers, which can seep into the ground. It is stored in aquifers. We will be dealing with aquifers later on, which are underground layers of rock or sediment that hold water. Aquifers vary in depth, thickness and permeability as well. We will be also looking into the idea of porosity and permeability. So, groundwater is replenished through your recharge, which occurs when precipitation of surface water infiltrates into the ground and refills the aquifer. So, groundwater and surface water are often interconnected, with groundwater, for example, discharging into rivers, lakes and wetland, and surface water also infiltrates through the ground to recharge the aquifer. So, you see there is a continuous interchange of the water, your fresh water between your surface water and groundwater. So, groundwater now I can say is the subsurface water occurring within the zone of saturation, which is part of the hydrologic cycle. We will be looking into this in detail, but just to define what groundwater is, it is the subsurface water again occurring within the zone of saturation, which is part of the hydrologic cycle. Now, when a river, because we have seen that a river and groundwater continuous exchange water. So, that is why when a river is gaining water from the groundwater, the river is effluent in nature and the groundwater becomes influent in nature. Whereas, if a river is losing water to the groundwater, then the river is influent in nature and the groundwater becomes effluent in nature. So, there are several importance of studying groundwater and the means uses of groundwater. Just to refer a few, that this is definitely there is more groundwater than surface water globally. We can't directly see the groundwater. That is why there is a misconception that obviously groundwater is very less and surface water is much more, but it is just the reverse. Actually, the groundwater is much more in comparison to the total quantity of surface water we have on earth. So, your groundwater is sustainable and reliable source of water because it is generally pure in nature. So, groundwater is less vulnerable to pollution because it is sitting somewhere deep beneath the earth. Groundwater is less expensive and economic resource. It is of high bacteriological purity. Groundwater needs little treatment obviously because of its purity before its use. Groundwater is usually universally available as well. So, groundwater has no turbidity, that means it is lamellar in nature because there is no turbulence in the groundwater, like we discussed about laminar flow and turbulent flow earlier. So, groundwater resource can be instantly developed and used. Groundwater has no conveyance lost. Groundwater has low vulnerability to drought as well, even in kind of desert region where you are looking into an oasis. It is nothing but where your water level is cutting the surface. That is why or that is how an oasis gets formed. So, groundwater is a source of dry weather flow in rivers and streams, and groundwater has distinct health advantages as an alternative for lower quality surface water. So, you can see we have to depend on groundwater for starting from your drinking purpose, be it your regular household activities, or even when you are looking for some pure water to be applied or to be used in some kind of industrial process, then also you have to rely on groundwater more than that of the surface water. So, now like I was mentioning that groundwater obviously a part of your hydrologic cycle. So, here is a simple diagrammatic representation of your how your hydrological cycle is going on. That, for example, if I start with the precipitation, your rainfall is going on here, and then the water is sweeping away towards the ocean. It is getting evaporated and condensed, and again it starts to develop clouds and prompting rainfall. Similarly, some water which is not directly sweeping into the ocean, it gets infiltrated within the subsurface, and that also forms this groundwater. So, you can say that groundwater is also a part of this hydrological cycle that is present. So, if I now look at this very specific diagram of hydrological cycle, then I have two end members here, the atmosphere and the lithosphere, and within this all your groundwater or your freshwater activities are constrained actually. So, if I start with this, from atmosphere, precipitation is going on the land surface, and also evaporation is also going on from the land surface. There is some interception loss during the precipitation when your water or rainfall is getting trapped within the tree leaves. So, that is also known as the interceptal water or the loss, because it will be directly transpiration will take place from the leaves of that water. So, what will happen that there will be a loss in the total precipitation that otherwise it would have been more in case there is no trees in a particular area. So, that is your interception loss. So, you have this water in your land surface, also some evaporation is going on. So, whatever is left on the land surface, that tries to infiltrate the soil. Also during that process also some transpiration goes on, and from soil again the water finally infiltrates into the groundwater body deep beneath the surface, upper surface of the earth. There also your transpiration process takes place, and the groundwater body is also supplemented by the magmatic water that is coming deep within in the ground. For example, magmatic water are generally associated with some kind of igneous activities, like we have discussed earlier. In case of igneous rock and volcanic activities, there is also always water is associated with this molten magma that is moving or coming up from the mantle. So, in that case you can also get some supplement of the magma water into the groundwater body. Then the land surface, from the land surface there is continuous outflow of the water into the stream, same as that the outflow will be from the soil towards the stream, and there will be again this interconnection between the groundwater body and the stream water, that there will be both outflow and inflow depending on whether the groundwater is influent or effluent, like we discussed. So, depending on this, outflow and inflow will go on. Then again with respect to the stream network, in stream network also precipitation and evaporation both are going on along with this interaction with the atmosphere, and whatever is left finally from the stream will run off into directly into the ocean. Again there also your both precipitation and evaporation is going on, and your stream network as well as ocean is also getting supplemented with your magmatic water. For example, if I look at the mid oceanic ridges where your basaltic lava is getting poured onto the surface of the earth, means you can say in the ocean floor, there also along with the lava your water is also pouring into the ocean floor. So, there is a continuous supply of your magmatic water down from the lower level of the lithosphere or even sometimes from the mantle. So, you can see there is a cycle that goes on and on like this, and there again there is a kind of a balance which is getting maintained, just like that of the rock cycle, just like that of the supercontinental cycle, Wilson cycle, like again and again we have discussed different cycles in our overall understanding of this subject. So, this also goes in a cycle like this. So, you have to only remember the interaction between the atmosphere and lithosphere and the intermediate members like the land surface that plays an important role, soil obviously that serves as the medium of the infiltration, and finally where your water is infiltrating and forming the groundwater body. So, this is extremely important. You have to remember this hydrological cycle if you are dealing with both in case of surface water or you are dealing with your groundwater. Then obviously like I was saying that your groundwater is present in the zone of saturation. So, that means that if I just now look at a cross section, then there are zones within in the soil or in the subsurface where there is a zone of aeration, that is also referred to as the vadose zone or the unsaturated zone, where your pore spaces that are present within the fragments or within the grains or within the sediment, whatever pore spaces are present, they are not completely occupied by your water. They are occupied sometimes only by air, sometimes also partially air, partially water, but they are not saturated in terms of the water present in the pores. But if I go down a little bit more towards the groundwater body, then what will happen? You are entering the zone of saturation. Now here every pore is actually saturated with the water that is occupying the pore spaces within the particles that are making up this zone of saturation. It could be rock fragment, it could be sediments, whatever it is, but it will means all the pore spaces in the zone of saturation will be completely occupied by this groundwater. So now if I say what water table is or the groundwater table is, then I can say that it is the upper surface of the zone of saturation, below which all the pores are saturated by the groundwater, and above of the water table there are also obviously there are pores, but in that case they are not saturated completely by water. Even there are pores which are only filled up with air. So in that case that becomes the part of zone of aeration, and this becomes the zone of saturation, and in this level that marks the upper part of the zone of saturation is your water table. So now if I want to define water table physically as well, so it is the upper surface of the zone of saturation, like we were talking, zone of saturation, where the hydrostatic pressure is equal to the atmospheric pressure. So your pH will be equal to Pa. So that's how you can physically define in terms of your hydrostatic pressure and atmospheric pressure, that this is the water table, or you can say the water level, that is the top part of means your groundwater level, that is the top part or top surface of your zone of saturation. So parts of your water table, it includes capillary fringe, vadose zone, and obviously the saturated zone. Again and again I was referring to it. So you have this kind of an unsaturated zone where your mostly it is dominated by your air. A little water might be present because infiltration is going on through these zones. Finally means you also have this zone that is the region just above the water table, where water is drawn up from below due to capillary action. So that is the capillary fringe zone. Then the saturated zone, that is completely occupied, all these pores are completely occupied by your groundwater. So now here again you have these two terms, that is porosity and permeability, and so if I say that a rock is having very high number of pores, or a zone is full of pores that are present in it, I can say that zone possesses a high porosity. It is simply the number of pores that are present in a particular area. And the permeability is again nothing but simply I can look at these two diagrams and I can say that first one, this one is the pores that are present, they are occupied by water. Here I will say that it has high porosity because the water is filled within the pore spaces. But if I refer to permeability, then I have to look for the interconnected pores, so that the water can flow through the interconnected pores. So that what permeability means. So the presence of interconnected pores determines the permeability of a rock, because that will control the flow of the water or whatever medium you are using, the flow will be getting controlled due to this permeability. So again if I say that just to look at the porosity and permeability, so your porosity of this one with no pore spaces will be very low, and this one, the last end member with this high pore spaces in it, will be of high porosity percentage. So I can simply calculate it by the volume of voids by the total volume of the material into 100. So it is also expressed, always expressed in percentage. There are two types of porosity, primary and secondary porosity. I will not go into very detailed discussion of it. but your fracture porosity generated by presence of fracture or cracks. Vagi porosity, it formed by the dissolution of soluble materials. Solution porosity arises from the dissolution of minerals, and karst porosity occurs in limestone and other carbonate rocks due to the dissolution of calcium carbonate by acidic water. So, this thing you should remember, because we will be dealing with this in karst when we will be discussing about karst topography as well. So, your karst porosity occurs in limestone and other carbonate rocks due to dissolution of calcium carbonate by acidic water. So, you can see these 4 types of porosity, secondary porosity in these 4 schematic diagrams. And you can also express porosity in terms of macroscopic and microscopic. So, macroscopic porosity simply means which is visible through naked eye, and microscopic means it requires microscopic observation, so that you can assess the pores that are means micropores that are present in a rock. Similarly, based on the connected and disconnected porosity and what actually regulates the permeability of a soil or a rock, it simply so your connected porosity, pores that are interconnected allowing fluid flow through the rock, and disconnected porosity, pores that are isolated from each other limiting fluid flow. So, that means if there is connected porosity, then that rock will have high permeability as well. If it is disconnected porosity, then that rock will be of low permeability. Simply like again these 3 diagrams, here you have no pore spaces, not permeable as well. Here you have pore spaces, but they are not connected, so that is not permeable again. Now, the third one, you have pores as well as they are connected, so that becomes a permeable rock or a permeable bed or strata. So, now before I end my first part of discussion on groundwater, which is I will simply discuss about this diagram, and this will clear up your idea about how this porosity and permeability are actually controlling the occurrence of aquifers and other types of aquiclude, aquefuge, these things. So, I have this triangular kind of a diagram here. Why triangular? Why not a rectangular one? If I would have a rectangular one, for example, if I simply draw this here, I will take this ballpoint pen. Yeah. So, if I draw this one like this, then I can say that there will be a position in this corner particularly where you will get a scenario where there is very low porosity but very high permeability, but that is not possible naturally, because if a rock is not porous at all, then it can't be permeable in any case. So, that is why you do not have this other side of this rectangular graph, and it becomes simply by eradicating this possibility, eliminating this possibility, it is simply your this triangular diagram where you have this porosity on one side and permeability on the other side. Will come to this weathering in a bit. So, here if I again simply remove this this part here. So, now specifically I will be looking at this diagram. So, here you can see on one side you have vertically going high permeability and downward low permeability. Again on the basal side or on the base, you have towards left you have very low porosity, towards the right you have very high porosity. So, now if I am looking at this zone particularly where your porosity is high, somewhere here I am looking, your porosity is very high as well as your permeability is also high. So, in that region what will happen? That the groundwater can be stored in the pore spaces, it can be also transmitted through the permeable layers, because it has both high porosity, so that it can store groundwater, and as because of the high permeability what is happening, there are connected pores in it. So, it can also transmit the groundwater from one place to another. So, in that case what you will get? You will get an ideal aquifer kind of situation. So, in case of ideal aquifer, I can think of examples like sandstone, a sedimentary rock, then coal, sands and gravels, and all highly weathered rocks, which have always will be coming to some examples about that as well later on, which have always high permeability. On the other end, if I look at now this end, here you have low permeability as well as low porosity. So that means you can't really store much of water, neither you can transmit much of water. So that's why in this part you can think of a situation that is ideal aquiclude situation, where you cannot store actually much of water, only little water can be stored, but not at all, you can't really transmit any kind of water through that region. So that what becomes your aquiclude. Also the probability of storing your water is extremely low because of very low porosity in that rock. Again, it reminds me of rocks like your fresh igneous rocks, then metamorphic rocks, and also your, for example, limestone and granite. So we will be talking about granite a little bit more, but here also to remind you about your limestone, that are chemically derived non-clastic rock. So they are extremely well cemented in nature. So the probability of having limestone with high porosity is quite low. So in that case, now you have granite, which is again composed of your quartz and feldspar, and they also exhibit an very strong interlocking kind of a texture. Directly, if you can refer to our discussion on igneous rock earlier. So now if I think of a granite which is otherwise an aquiclude, because it has extremely low porosity and almost no permeability, in that case it will behave as an aquiclude. Now the granite, after a period of, for example, a few thousand millions of erosion, that granite is now exposed on the surface of the earth. So what will happen? Obviously it will be going through a process of both partially mechanically but highly chemical weathering. It will go through because of the rainfall that is happening on the top of the granite. Also some mechanical weathering due to the unloading and due to some thermal expansion, like we discussed when we discussed about mechanical and chemical weathering. So now this granitic rock, which is supposed to be strictly a aquiclude type of rock in nature, this will go into weathering, both mechanical and chemical. It will lead now to the, for example, transformation of the feldspar minerals into your clay minerals. So now you can say you are now losing this interlocking kind of texture or interlocking nature of the quartz and feldspar grains that were present in the granite. So now after this you are increasing the porosity. When it is subjected to this kind of both mechanical and chemical weathering, it is enhancing in its your porosity, as well as the permeability likewise is also getting enhanced along with it. So now a granite which is supposed to be an aquiclude can become an aquifer over the time of weathering. So this last part of this right angle triangle is this arm is your weathering. So weathering has a significant role in transforming an aquiclude into an aquifer. So this understanding of this triangle is very important whenever you are dealing with these terminologies or your types of this aquifer, aquiclude, and when these are getting controlled, nothing but due to the porosity and permeability of the layers. So the last thing that I want to mention as well, here there are also some aquiters with you can say medium permeability, medium porosity. We will be discussing about that as well, but what I wanted to mention is the presence of shale here. So shale is, like we discussed, obviously it is a sedimentary rock, but it is such kind of a rock that it has very high porosity, but there are almost no interconnected pores in the shale. So the pores are restricted within the layers of a shale. So that's why there is almost no permeability in shale, but very high porosity in shale. So that's why they are also not very you can say ideal rock to store, means you can say to extract groundwater, because though they can store groundwater, they will not transmit groundwater. So that is a problem with shale. So here I would like to conclude with the first part of our discussion on groundwater. Next we will be moving into the second part of our discussion. Thank you.